No?
Well, good afternoon. I'm David Kankam, the Center University Affairs Officer at NASA Glenn. It's my pleasure to have all of you today for the third of our series of presentations that will help you with the design challenge. Today we've got two presenters. The first one is going to be on cryogenic fluids management. That will be followed immediately by in-space propulsion. The first speaker is going to be Mr. Wesley Johnson, who is a lead technologist on Evolvable Cryogenics Technology Demonstration Mission here at NASA Glenn. His research engagements include the following: thermal characterization of installations, as well as integration of refrigeration systems with cryogenic tanks. Mr. Johnson received his Bachelor of Engineering in Aerospace as well as Masters in the same discipline from Auburn University and University of Central Florida, respectively. He started his NASA career at Kennedy Space Center in 2004 and has been at Glenn Research Center since 2014. He's a member of a number of professional organizations, including AIAA and other well-known societies. And it's my pleasure now to have Mr. Johnson make his first presentation to us.
Yes, no questions.
If you have any questions, we've got just below my picture there the webcam where you can send all your questions, and we'll try to answer them at the end of his presentation or the second presentation. So, Mr. Johnson.
Thank you, Dr. Kankam. So I'm here today to talk to you about cryogenic fluid management. Later today, Rex will be talking about in-space propulsion. So cryogenic fluid management is how we handle cryogenic propellants as they are going to be used either in space or on the ground for propulsion applications or even other applications. So
Just a minute, you bring up PowerPoint.
So bring up the charts here. So cryogenics is it's the study of low temperature fluids. And generally when we talk about cold temperatures, we're referring to temperatures below minus 150 degrees C or 123 Kelvin. Some of the fluids that we use are shown on the temperature plot on the bottom of this chart, and you can see the relative temperatures of nitrogen, which at ambient pressure boils at 77 Kelvin or minus 321 degrees Fahrenheit. Hydrogen, which is one of our favorite propellants, is at 20 Kelvin or minus 423 degrees Fahrenheit. And then some of the applications that we use for science observatories are just above absolute zero at minus 459 degrees Fahrenheit. The word cryogenics comes from literally to produce frost, and generally when we run cryogenic testing, we produce a lot of frost and ice. So there's several different reasons that we use cryogenics at NASA. The first is for propulsion. Liquid hydrogen and liquid oxygen combined have the most efficient propulsion from a chemical perspective, and but they're also the lowest temperatures. And for example, hydrogen expands over 800 times between when it's a liquid and an ambient temperature vapor. So if we'd have tried to launch, for instance, the space shuttle using ambient temperature vapor, hydrogen and oxygen, it would have been about the size of the width of the picture. You can see the shuttle at the bottom there. Also, hydrogen is very useful for nuclear propulsion, which is the other picture you see there. And it's one of the main propellants that is used when nuclear propulsion is discussed. The other application that NASA uses cryogenics for is low temperatures. So various space telescopes, such as the Hubble Space Telescope or the James Webb Space Telescope, which you see at the bottom left picture there, they operate at very low temperatures. For instance, the entire spacecraft of James Webb will operate around 35 Kelvin. Also, the picture in the middle there is the Astro H or Hitomi Observatory that was co-developed by JAXA and NASA, and that had sensors on that operated as low as 50 millikelvin, which is very close to absolute zero. When we start discussing different cryogenic fluid management technologies, then we start looking at a wide variety of systems that all fit together to make an upper stage or a propellant tank work. First, you have the thermal control in the bottom left-hand corner, which provides the energy that causes all the problems for cryogenics. Because cryogenic fluids are such low temperatures, it's inherent that we minimize the energy that gets into the tank, because the tank causes the cryogens to want to boil, just like you have water that boils on the stove when you put heat into it. And so in order to prevent the tank from exploding when the propellant starts to boil, we have to have a vent system on top. If we don't vent it, then the tank self-pressurizes, and that is often referred to as pressurization. Also, while we're working with the fluid, we need to know how much propellant is in the tank, so we need to have various types of gauges that tell how much propellant is in the tank, and we have to be able to get the propellant out of the tank, so we need to have various devices that go inside the tank and help to expel the liquid and get it out of the tank as we need to use it for an engine. We're starting to look at various applications of refrigeration, which is just like your refrigerator that you might have at home. And that's where we actually remove the heat from the tank, and so we'll use a refrigeration cycle, which is just the opposite of a thermodynamic power cycle, and run it backwards, and we can actually remove energy from the tank. However, that also requires us to put lots of input power into that refrigeration system. So just like you plug a refrigerator or a freezer into the wall to draw power out, we have to plug our refrigeration systems in to get power and to remove power. And so, for instance, on a liquid hydrogen system, you may have to put 60, 70, even 100 watts of power into the refrigeration system just to remove 1 watt of heat at 20 Kelvin. We also do a lot of mixing and destratification, because as the heat goes into a tank, the fluid acts as a capacitor and a energy storage device, and so the energy wants to stay as close to the tank wall as it can, and so that causes the pressure, the temperature of the ullage gas to increase much quicker than it normally would if the energy was more evenly distributed in the tank. And so by mixing the tank, and I'll show you some videos of some applications of that in a couple minutes, then we can actually prevent the pressure from rising as quickly. It's also good for us to be able to know if there are any leaks around the tank or any valves that might be around it, and so we do leak detection around a tank and associated components. And we also do a fair amount of study on how quickly you can fill a tank. And if you start with a warm tank and you put cold liquid in it, it means you have to chill the tank down, and so filling and chilling the tank is also important. So based on that, I'd like to talk just a couple examples of technologies that we work with here and how they apply to various propulsion systems. So first, I'll just talk about some of our numerical analysis or computational fluid dynamics applications. Then I will talk a little bit about a special technology called the radio frequency mass gauge. And then I'm going to talk a little bit about how we might produce propellants on the surface of another planet.
Am I wrong? Did you want to comment on what was going on in the picture at the bottom?
Oh, sure. So the video at the bottom just shows a test setup that is being prepared. That's a time-lapse camera, and we took, I think there was about a 2-week time period. You can see how the experiment goes together, and there's a lot of different people that come in and work on it. There's a lot of different things that have to go together even for this small experiment to make it work well. Okay, so first let's talk a little bit about numerical analysis. There's a couple different types of numerical analysis. One of the most popular types of numerical analysis that a lot of people like to do is computational fluid dynamics, which is also known as CFD. This is really good for fine, detailed analysis and to understand the very intricate details that might go on. So in the picture on the right, you can see a time shot out of a CFD analysis that we did. And can you make the video play at the bottom?
Yep.
Also at the bottom, that video is an example of a mixing jet that is penetrating into a bubble. The experiment was actually run in the 1990s on the space shuttle, and we're finally getting to the point where you can actually coherently model it in CFD and make the CFD bubble look close to the bubble that was in the original experiment. We also do nodal or lumped analysis, which is, if you think about CFD as having an extremely fine grid, it may have a million grid points in a single CFD run. A nodal analysis or lumped analysis may have 5 to 10, maybe 20 lumps in the analysis. And so this is good when you want to run things for long durations, where we may be looking at, say, months or even years of operation on orbit or in a mission, and we need to know how the system will react over the whole time. So as you can see, the CFD video is actually looping, and so it's about 15 to 20 seconds of CFD time, and that's pretty much as long as we can run for some of the more refined grids. And then the picture at the bottom there, you can see as we've slowly improved our CFD capabilities over the last 3 to 5 years, the first time we ran it, we had the black line. The second time we had the blue dotted line, and finally the third time we ran and made some improvements into how we treated the two-phase aspects of the spray you see above. Then we were able to hit the pressure decrease of that experiment much better than the first 2 times we tried. So as you can see, sometimes CFD takes a lot of work into actually developing the physics that are in the code, especially when you're talking about cryogenic fluid dynamics. Okay. Oops.
Oh, we go.
There we go. And so this video is another video from the same experiment called the tank pressure control experiment. And you can see this mixing jet right here, which is penetrating all the way through that ullage bubble. The ullage bubble is the spark thing that's sparkling in the left-hand picture right there. And it's the yellow on the CFD simulations. And you can see how the gravitational, the microgravity allows the jet to completely penetrate through the ullage bubble, and due to the various gravitational perturbations on the shuttle, the ullage bubble actually moves around, and it's a very dynamic event, and it's really cool that we can actually get this modeling to pan out right now. A whole team of people spent a couple years trying to develop the tools to get to where we could get to this point to have these videos. All right, the next technology I'll talk a little bit about is the radio frequency mass gauge. So similar to the way a tank responds on a vibration table, and to where you can have natural frequencies due to vibration, you have natural frequencies in a tank in the RF spectrum. And these natural frequencies within the tank and the RF spectrum actually change as a function of how much propellant is in the tank. So we can use these different spectrums and look at where they occur and track how they change and know the liquid level within the tank. So by taking a snapshot of the frequencies at a given time, we will have run previously a bunch of simulations so that we know exactly how the tank should respond, and and we can compare the real tank snapshot to the simulations, and then doing a regression model determine the approximate fill level of propellant in the tank. And so this is really important because when we have propellant in the tank, when we go to do various burns, we want to know how much propellant is left, because if you run out of propellant in a tank, then the engines don't really like that and can misfire and blow up. So it's really important to know how much propellant is in your tank before you go to do that fire. And a lot of satellites also, because they do a lot of small maneuvers, they try to keep track of how much propellant is in their tanks, and that allows them to know how much more firing they can do. And most satellites actually end their service not because they ran out of science to do, but because they've either run out of propellant in the tank or some other part of the spacecraft has failed first. So it's important to know how much propellant is in your tank. Okay, the third snapshot I'd like to give into some of the research that we do is on liquefaction of in situ resource utilization of produced propellants. I know that's a mouthful. In situ resource utilization, which is ISRU, is simply making stuff where it is. So when you go to, say, the surface of the moon or the surface of Mars, you use what is already at the moon or already at the Mars, in this case, to produce propellants. So right now, in NASA's journey to Mars, one of the key considerations, as you can see in the bottom graph, is that we can cut the lander mass in over half for descending it first from launching from Earth and then descending to the Mars surface, if we can make all the oxygen that we need to come back on Mars. If we make the methane, we can cut another 10 or 15% off the lander mass. But the big hit for Mars applications is the oxygen. And so that means we have some sort of chemical process. Maybe it's a rover, or maybe for just oxygen it can be a stationary platform, like you see in the picture. And we have to take it onto Earth, what would be a liquefaction plant, or a chemical processing plant, which you see a picture of right there. And in that plant, we will take the oxygen gas that is generated, and we run it through a series of heat exchangers and liquefy the oxygen gas. Then we dump that liquefied oxygen into your Mars lander, as shown right here. And so there's 4 tanks, and we have to fill up all 4 tanks. Oh, and that oxygen production plant has to fit on the lander too. So we don't get the big, huge oxygen production plant that you would have on the surface of Mars. And so on the right-hand side, you see this small version of the lander with all the panels sticking out of the side. And those panels are for producing and rejecting power. So you can see just how intense of a power mechanism, how power intense some of these processes are. And so, as I mentioned, for hydrogen, a refrigerator at hydrogen temperatures usually takes 60 to 80 watts of input power per watt of heat rejection, whereas for oxygen or methane, we think we can get below about 10 watts of input power for every watt of refrigeration. So if each tank has, say, 50 watts of heat input, that means we need 500 watts of power generation just to be able to reject all that heat. And then we also have to take care of the phase change, or the heat of vaporization, which is also fairly large for cryogenic propellants. So those are some of the challenges that we are working on, and we're working on a lot more than that, but that was just 3 challenges that I could give a fairly quick overview of. And I hope you have an opportunity to submit some questions that I can answer to the email address below. And so just in summary,
No questions at this time.
okay, so we don't have questions yet. But so in summary, basically what we're trying to do within NASA is create a way that we can both produce propellant in space and also store it for fairly long periods of time, up to a year. And so we want to create essentially gas stations in space. Because when you go on a road trip, you don't take all the gas that you need for the road trip with you. Otherwise, your car may look like the car shown here, where you have various drop tanks where you just have to refill your car's gas tank. And so since currently this is how we do all of our missions, and that we carry all the propellant that we need to do the mission with us from the start, and we're looking for ways that we can not have to carry all the propellant with us from the start, whether it's from pre-positioning, various satellites or stations with propellant that are stored or produced on them, or even producing the propellant on various destination surfaces like the surface of Mars. And so with that, cryogenics is a very exciting topic. It's enabling exploration and learning, because we not just don't use it just for propulsion. We also have used quite a few cryogenic systems on almost every observatory and telescope that has launched over the past 30 to 50 years. Nearly all of them are cooled by some type of cryogenic system, whether it's only to 77 Kelvin with a liquid nitrogen system, or whether it's to 50 millikelvin with a very complicated cryogenic refrigeration system. So at this point, I guess we're still waiting for, if you have any questions, feel free to send them to the email address below. And it looks like we're gonna switch over to the next topic. Thanks for your attention.
All right, we're just about ready for the second speaker, who will speak on in-space propulsion. That will be given by Mr. Rex Delventhal. He's the Deputy Functional Area Manager for Orion Crew Service Module Office here at NASA Glenn. And in that capacity, he provides leadership, project management, resource planning, and technical guidance in the design, development, test, and verification of liquid propulsion systems on the Orion aircraft. Mr. Delventhal is a holder of Bachelor of Science from University of Cincinnati, and he's a former employee of GE Jet Aircraft and also Johnson Space Center in Houston. He's also, like the first speaker, a member of a number of professional organizations, including AIAA. And it's now my pleasure to call on him to present his part of the speaker series. Mr. Delventhal.
Thank you, Dr. Campaign. Well, I'm here to talk to you today about in-space propulsion. And for many of you out there, that could mean many different things. So I want to talk in terms of what in-space propulsion is, and then get into the many facets, and also relate what you just heard from Wesley, did a fantastic job talking about cryogenic fluids. So,
Okay. Back one. Here we go.
So just to set the stage for what is in-space propulsion, well, in the most simplest terms, is how we provide motive forces to be used by spacecraft to maneuver in space. You know, when you watch a rocket launch, you think about the booster that kicks it off the Earth's surface and get into space, but really, that's the starting point for us to talk about in-space propulsion. When that launch vehicle completes its insertion of its payload into space, in-space propulsion is what you have on the vehicle, on the spacecraft, to provide primary propulsion, both for steering, attitude control, pointing the spacecraft, and then for providing a delta V or energy to change the orbit and move to a different orbit, that kind of thing. So that's, you know, it's a very simple starting point, but just to set the stage for what we're talking about throughout this discussion. So how to get around in space? Again, if you look at this picture on the left, which is just a simple diagram of the Earth going in orbit around the Sun, and the spacecraft that first initially gets into Earth orbit. It may be a spacecraft that's doing Earth science, so it's going to stay on Earth orbit, but it needs to have ability to make small adjustments or point to different targets. It may be a spacecraft that's going to go to the moon, and so we need to make a trajectory change to put it on a path to go from Earth an orbit out to the moon. So that's an energetic need to put into a new orbit. A higher energy need might be to go to Mars, and so you see a trajectory to go out to Mars, and so a spacecraft that's going to do science at Mars is going to have a propulsion system to get there and do this mission for that duration. There could be other needs, that, obviously for outer planets, that kind of thing. So bottom line is you need a rocket engine to do that job, and so in the picture on the right you see a very simple diagram of a rocket engine making thrust, and it does it, in this terminology, in this picture, we're using an oxidizer and fuel that are ignited and combusting to generate high temperatures and therefore exhausting that gas out the rocket engine to make thrust. So your thrust equals mass times acceleration. It also is, or another term is the mass flow of the propellants times an exit velocity, how fast we can get that gas out the rocket engine to generate thrust. So those are the terms that are very elementary to what we do in designing rocket systems. Now, on the lower left, you can see in the box a very important equation, which is a metric to assess the efficiency of a rocket engine. That ISP is a term called specific impulse, and it's the relationship between the thrust that the rocket makes and how much mass flow is going through it as a measure of performance. So the units boil down to measures of seconds, and so that's a little bit hard to grasp. And so the analogy that we often use is that ISP is kind of like the miles per gallon of your car. If you drive an old clunker that gets 10 miles a gallon, you're kind of jealous of the guy on the freeway driving a Prius at whatever that is, 30, 35, I'm not sure, but a higher efficiency engine is going to be more attractive, and so we look for systems that have high efficiency, high ISP, and the thrust that the mission needs to do the mission. So with that, I think we're ready to go to the next chart. And
Go ahead.
that. I'll go forward. Okay. On this page, this is a rendering of a early design of what we call a propulsion stage or a service module. This actually, from what my personal work is on the Orion program, and this is an early rendition of a service module, which is the propulsion stage to maneuver a crew vehicle on orbit. So to set some key terms, if you are going to maneuver a vehicle, obviously you have a main engine, and then you see the picture of it on the left there. The main engine is what provides the means to push a spacecraft in a different orbit, add energy to an orbit, take it to a higher orbit, that kind of thing. And if you look at this particular rendition of a stage using propellants, those tanks there are whole propellants that get consumed as you do a burn, and they could be different kinds of propellants. We're going to get into that next. But as that gets consumed, the center of mass of that vehicle can change and move as you're using propellants, and so we have to steer something. So there quite often with the main engine there'll be like a thrust vector control system that points the thrust vector actively to keep the thrust vector going through the center of gravity so the vehicle stays in control. In addition to that main set of propulsion hardware, you'll have smaller engines, we call them auxiliary engines or reaction control engines. They can serve as backups if the main engine has a problem and needs to shut down, and also to do other steering, pitch, yaw, roll control, that kind of thing on the vehicle. Because once you're in space, obviously there's no forces to work on, so we have to always work with nulling out rates and that kind of thing on the vehicle. Now, in addition, I want to emphasize a little different perspective, because people think propulsion is an engine, but it really gets into more than that. You've got to have tanks to store your propellants. You've got to have lines and valves and regulators to condition and feed engines with the propellants. You have pressurization systems to keep the propellant tanks at pressure. All those parts have to interact successfully, and that's just the propulsion stuff, if you will. The actual full spacecraft will have other things with it, structures to hold everything. There's power systems to run valves, instrumentation, guidance and navigation and control, the software that allows for the burn calculations and what it needs to point. Thermal control, depending on the type of propellants, it may need to be heated, it may need to be cooled. I'll touch on that in a few seconds as well. Safety and mission assurance are considerations because we're dealing with very energetic systems that have hazards, that have a lot of things to be controlled, and so all those factors play into designing and operating a flight propulsion stage. So just a lot of things to chart with a lot of pictures, but it really sets the stage for what in-space propulsion encompasses and how we leverage the advanced development that Wes talked about with cryogenic fluid management. The suite of biofluid areas that Wes did a great job talking about on the blue boxes I deal with, for the sake of cryogenic propellants, how we condition them to feed an engine, from a cryogenic standpoint. That's one class of chemical engines that we use in the massive suite spacecraft. Now I want to switch over and talk for the propulsion systems. We generally have three classes of propulsion. On the upper left, you see a bubble for chemical propulsion systems. These are systems that employ fuels, oxidizers that combust in an engine and produce thrust that way, and that has a certain set of characteristics to it. There are non-chemical systems on the lower left, and these are systems that produce thrust differently, either through heating gas or creating an ion field, magnetic field, like electric propulsion does, or solar sails, those kinds of technologies that do a whole different class of in-space propulsion missions. And then there's another class of advanced propulsion, things like beamed energy, fusion, breakthrough technologies that are not really flight systems today, but there are groups within the agency working advanced propulsion systems that we hope to mature down the road. There's a particular class I'll touch on towards the end of the presentation down at the bottom there about nuclear thermal, which is a very unique aspect. Again, Wes touched on it briefly in his talk. It's a very unique capability that has performance that I'm going to try and explain a little bit in the next shot, next slide. Before I leave this one, back in the chemical start, when we start talking about that, there are solid propellants, propellants that are contained as a solid. They do a specific type of burn. My experience has been in the storable propellant systems, which are used to extensive use on a lot of spacecraft. There's features about that are advantages, like being able to be stable on room temperatures. Ignition systems are not needed for the kinds of systems that we call hypergolic, where the fuel oxidizer wants to react as soon as they come into contact. So there's a simplification of the systems to fire engines with that aspect. There's non-propellant systems, which will only need one liquid propellant, a fuel that's decomposed over a catalyst bed. All those engine types, if you will, have advantages and disadvantages, and that's really important as we go through this discussion. And again, the cryogenics, the liquid oxygen, liquid methane, liquid hydrogen, all have combinations of performance characteristics that we need to consider. Okay. So on this chart, I wanted to just relay a history perspective. I'm not going to go into this in a lot of detail, but on the bottom, clearly you've seen the success of NASA in the manned space flight programs from Mercury, Gemini, Apollo, the Space Shuttle program. Those systems on orbit, in-space systems, typically employ, as I mentioned, the storable systems, the hypergolic systems, the solid systems, to maneuver the vehicles in space. These are generally pretty large craft to support crews in space. They have mission durations that range from days to weeks, obviously, and so we have systems that provide that kind of mission capability. Up above, you look at a suite of unmanned spacecraft that NASA's produced over the decades, and again, spacecraft that went for explorations to the moon, to other planets, also used similar propellant systems. But as you start looking on the right, you start looking at missions like DS-1, Deep Space One, Dawn, missions that now go out further in the solar system that have more energetic needs, more what we call delta velocity requirements. And so all of a sudden, the chemical systems start to lose favor because there's an intrinsic limit in terms of how much you can get out of the chemicals. So we start looking at electric propulsion for those kind of spacecraft, and you'll see why in a few minutes. So we've taken broad cut at the many spacecraft that have flown, and you see quite different uses of the system. Okay, on this chart, I wanted to spend a minute talking about the engines, the business side of how we make thrust. For every engine type, whether it's a hypergolic engine, a solid motor,
that kind of thing. You've got to have advances in many different areas. In the areas of combustion temperatures, we've looked at material enhancements to have higher temperature capability, engine stability to make engines burn in a stable pattern, so that the technology to make that very stable operations. There's been work when you go from what we call pressure-fed engines, which are relatively simple. We just feed them engines at a relatively moderate pressure to combust in the chamber, to higher performance using pumps. Upper stages typically will use a pump-fed engine that require rotating machinery with blades, turbine blades, and bearings, and a lot of techniques and technologies for pump life have been worked on over the years. And in the case of other propellants, we've made strides to advance both. As an example, in monopropellants, the workhorse for many decades has been like hydrazine as a monopropellant, which is well characterized, very often used. A downside to it, though, is it is a toxic propellant. So there's been work over the years to develop non-toxic propellants, which have very comparable, if not better, slightly better performance, but don't carry the burden of hazards to ground people that have to process the spacecraft. And then in more recent years, if you look on the right, there'll be a couple pictures of working in the propellants of liquid oxygen and liquid methane, again touching on some of the stuff Wes talked about for using new engines with propellants that work in the in situ utilization missions. So we did work to develop engines of the thrust levels that we kind of use for manned spaceflight, both as a main engine and as a smaller steering engine, what we call a reaction control thruster. So on the next chart, I'm going to show a short video. First is going to be a video, and this is for you students that enjoy fire and smoke. This should be attractive. This is a video now of a main engine using LOX methane demonstrating operation at those kind of conditions. That was a sea level test. This will be a test at called altitude conditions at vacuum environments. Obviously, you're seeing the nozzle start to radiate the heat. The chamber itself can be cooled with propellants, but the nozzle radiatively cools. And that is backflow from the shutdown, basically because we're firing into a vacuum system that when we shut off the engine, there's a backflow. Now that was a video of a 5,000 pound thrust class engine, a main engine that have a burn durations of minutes to create a delta V. This next video now will be what we call an RCS thruster, a 100 pound class thruster that is more of a steering engine. So this is more of a pulse mode engine that we were developing. And in this video, you see it pulsing as opposed to the main engine, which was more of a steady state firing. And again, the same, engine now at altitude conditions. Okay. I think, when it comes down to propulsion, it's always fun to see the end effector doing its work, and so that was a couple videos to give you a sense of that demonstration. Okay, so the next question is, when I talked about all those propellant combinations, why don't we just always use a chemical rocket? Well, when is chemical propulsion not enough? This chart tries to explain figures of merit when we don't want to use a chemical rocket. The physics of spaceflight says there's a rocket equation that relates the initial mass of what you put into space to its final mass, and it's got a function of how much delta V, how much energy the mission is going to require to do its job. It's the exhaust velocity of the propellants of the rocket engine. And so the goal, if you will, is to have a high mass fraction. You want to have, if you're a crew on a vehicle, you want to have your ship being mostly the crew vehicle. If you're a science project, you want to have the science the biggest part of your spacecraft. You don't want to be largely just carrying the fuel to do your mission. So the mass fraction, you want to optimize that, make it as high as possible. But if you look at that box of delta V's for different missions, depending on if you're doing a mission from low Earth orbit LEO to geosynchronous Earth orbit GEO, delta V's that for that mission are under 5 kilometers per second for that mission. You see that back to that chart on the right, when you and again, these are very sort of gross level comparisons between the black line, which is a performance metric for chemical propulsion, the liquid oxygen, liquid hydrogen kind of combination, 460 seconds, that capability to have a high mass fraction drops off very dramatically as your mission delta V goes up. So you compare that to what we call electric propulsion, which is a high ISP type system, and that's that red curve, and you see there's a much more friendly profile comparing the mass fraction to the mission delta V. So, if I show you that chart, everyone's going to say, why don't we just always do electric propulsion? Well, again, Murphy's Law says nothing's ever free. You don't get the benefit of that without some cost. And the most direct cost for that kind of system is while you do have a benefit of a electric propulsion system with high ISP, they do not provide the same thrust levels that we get with the chemical systems that you saw videos of in the examples I mentioned earlier. So when you have the need for a large mission delta V to go do much farther exploration type flights, but to get the payload that you want, and you employ an electric propulsion system, you've got to recognize the thrust levels now go from many pounds, thousands of pounds, hundreds of pounds, down to fractions of a pound, and really talking ounces of thrust for that type of system to work. So burns may be measured in months, if not years, for electric propulsion systems. Now, there's on the next chart now will be a description of the kinds of electric propulsion systems that have got a lot of heritage and flight history. EP uses heat to add energy to a working fluid, or electromagnetic fields or electrostatic fields to accelerate particles or plasma through the engine. So these systems now will be very different in terms of their architecture, how the spacecraft is configured to support one of these types of engines, and I'll give you one example on the next chart, which is an ion engine we call NEXT. This is a functional diagram showing what it takes to support an electric propulsion system different from what I showed you on an earlier chart of a chemical stage. If you look, some of the inputs, this is got a lot to it, but the term xenon supply, that's the propellant of choice for this kind of engine. You'll need far less propellant to feed this high-performing engine, but you'll feed it through a number of other components, and also you need a lot more power conditioning, because if you look at the performance metrics of this type of engine, the ISP looks fantastic, a high ISP. However, the thrust, again, as I mentioned before, is very low, so the trip time is going to be quite long for a system using a next type engine, and it's going to require a lot of power to feed that engine, kilowatts of power, versus metrically, hundreds of watts for a chemical system. That now ratchets up to kilowatts of power to feed an ion system. Not that that's it's a matter of trade-off for the mission you need to devote to develop relative to the kind of engine and the needs of that system to do its job. Now, I've talked a little, hopefully that made a little bit of sense in terms of when chemical systems are employed. Electric systems have benefits at some other cost. It got you thousands of seconds of performance, but very low thrust. I want to branch for a few minutes and talk about sort of a in-between, but very, very attractive system, and that's nuclear rocket propulsion on this next chart. Nuclear thermal propulsion is a very different beast, if you will. That's using a nuclear reactor as the heat source. Rather than electric power, it's going to be using a nuclear reactor to heat and accelerate a working fluid, typically hydrogen. And the fundamental metric, as we mentioned before, ISP, now for this class of engine now is going to be much higher than chemical. It's more on the order of 900 seconds of performance, so it's quite high in ISP, but again, not of the same scope as the several thousand seconds for electric. But the difference is now you do have a high thrust engine for the kinds of missions where this makes sense. The picture on the right is a picture of a NERVA engine. NASA was working with other government agencies through the 70s on a nuclear engine that had success up to a point. A lot of reasons why that was brought to a close, largely environmental reasons for testing nuclear systems on the ground, that kind of thing. But there are continuing studies that have gone over the years about how to still take advantage of this technology and use it again for enabling future missions down the road. On this next page, I will show you just a rendering of some past studies. And if you look at this, the idea being in today's environment of environmental restrictions, to work within those now, really it's taking the technologies for nuclear reactors and basically reducing the footprint, if you will, to go from engines that were 75,000 pounds of thrust, which that makes everything that scale. If we can work with engines that are lower thrust, still thousands of pounds, but now the engine looks quite a bit smaller in footprint. The test facilities to work those now are more manageable, so there studies are going on to make that come into being. But so you look at the enabling missions that can provide now. Now we kind of provide a whole different class of missions with nuclear propulsion, and that's something that's part of the NASA endeavors for future in-space systems. Okay, now in this chart I wanted to bring a little bit back to the beginning of the propulsion stage, if you will. So we like to talk about the engines because that's where we make the fire and smoke, but that all needs to come together. So one of the big things is to not just test the components, if you will, the engines, the tanks, the valves by themselves. It's really to pull all those critical components together, the propulsion system, how it also has to tie into everything else on the stage. And so what NASA works to do is to, in the end, before we ever commit a stage to actual in-flight operation, is to do as much integrated testing as we possibly can. So you see full-up stages tested in various past pictures. I'll show you next a short video of that one on the top. That Delta 3 is a stage that we tested at the NASA Plumbrook facility a number of years ago. And again, the systems that I'm working on right now is the Orion ship. So you see the early CAD in the middle there on the lower right. That's the earlier rendition. We have, in the recent years, NASA's joined with the European Space Agency to bring that service module as a contribution from the Europeans. So the lower right is our current rendition of Orion with the Orion, the European service module integrated with it, and that stage, if you will, is actually, as we are in the stage of component testing and bringing that integrated system from Europe to the U.S. to do that integrated system testing for that next vehicle here. That'll be happening later this year. So the stage there, the message really is just, in the end, is to prove out the reliability, the performance, the safety, the interactions of all the parts together in an integrated system test. So with that, we'll go to the next chart, and this will be a video of that Delta 3 upper stage as a full up stage, and you'll see the what I'm trying to relay in this video is the size of the stage really drives a lot of infrastructure, both in the test facilities that we need to test it, the logistics of moving a stage around to do this kind of testing. Okay, so this is a close-up of the engine nozzle, or, with operations. Take a different view, stepping back initially as the engine is delivered out to the test facility to give you a sense of the size of this. You see the large tankage, the engine on at the bottom of the vehicle, and it's being hoisted and lowered into a very, very large facility that can pull a vacuum, simulate the space environments, hot, cold, and no pressure, if you will, the lack of atmosphere to do the full stage testing. And people ask, what is that coming off the engine? The fascinating part of it is that this engine's burning oxygen and hydrogen, and the engine is very, very hot, obviously, as you can see, but because you're expanding into a vacuum, the drop in pressure drops temperature, and we actually form ice at the lip of the nozzle, so that's ice coming off the engine. So what you're really seeing is the culmination of once we've gone through all the step development of developing critical components, integrating them into a full-up system, we, to the best of our ability, test that end-to-end in as much of a spaceflight environment as we possibly can. And that's what gives us the confidence, reliability now to then commit to spaceflight. And in all that, I'm just trying to relay, with advanced propulsion, it's important, we're making great strides for future technology and future capabilities. We always want to look back to the past because we've really learned lots of lessons learned over the years. These are energetic systems, they have hazards. We need to not repeat mistakes and to have the best possible success to really make those systems in the future work reliably. And with that, that's hopefully in a very short presentation you've got a sense of the broad areas of propulsion, chemical, non-chemical, nuclear. There's more than that, but in the time that I had, this was the best chance to give you a snapshot of propulsion systems at NASA. So if you have any questions, be happy to take what you have at the email below.
Any questions? Okay, we don't have any questions. Dave?
No questions. Well, I want to thank all of you who tuned in this afternoon. If you don't have any more questions, just a reminder that the next speaker series will be February 20th, about the same time, 3 o'clock Eastern Standard Time. But when we log off here, if you have any questions, you can always send them.
22nd.
February 22nd, I'm corrected. So the next speaker series, February 2-2. Okay? And thank you all very much. If you have any questions, please send them to the mail address indicated at the bottom of my portrait there. I will try to answer them for you. Thank you.